All right, we're going to try this. So today we're going to be diving into a little bit more of sequences and series. We're going to introduce some interesting terms. And with any luck, we'll get into some money. All right. I always misspell this word. The Fibonacci sequence. Fibonacci sequence is all right. The Fibonacci, and we're going to go into this in a little bit further. But one thing that I'm very interested in making sure that you know how to do is to be able to describe a sequence like this. So what I want to be able to do is write a rule that will allow me to generate this list if I want to. Okay? Take a look at it and see if you can A, find the pattern, and then B, let's see if we can find a way of writing. Take a look. What do you think of it? Yeah. Tell me. Okay. All right. Now, if that is how you describe it in words, and it's right, what I want to be able to do is describe it mathematically. So, how do you think we might be able to do that? Yeah. Okay, let's do that. So, how do we begin? Okay, yeah, we're all guessing here.
The second term is different variable, so it will be so we say that if A is the previous term, B is the second.
Okay.
A becomes and then C as the answer. A plus B equals C. C plus E.
Right, and eventually we're going to run out of letters. I don't disagree with you. I like your thinking, but what I want to be able to say is, can I define this thing and say, all right, if I'm going to find the fifth term, yes, it's true, I need the third and the fourth. So let's see if, yeah. I like this already. Equals. So if I'm looking for the fifth term, if n is 5, well, now all of a sudden I'm going ahead of myself rather than looking behind myself. So what I'm going to do is I'm going to modify this just slightly because your thinking is totally correct. And in fact, I like your notation, but I'm going to modify it just a tiny little bit. So instead of looking ahead for values, I'm going to be looking behind me for values. For example, I could write it like this. Which is just slightly different. But in fact, this is great. This is excellent. But in order for me to do this, I first have to describe what are called base cases, okay, the very beginning of the proof. And to do that, you have to define them. The first number is 1. Is that all I need? No, I need 2 terms, right? I need, in order for me to go any further, I need to say the 2 numbers behind me. If I know that, now I can rock and roll forever. Okay. Now the Fibonacci sequence is found all over the place. And nobody really knows that it's there, but I promise you will never look at a flower the same way. So what I'm going to do is I'm going to pause this video and we're going to watch, I think it's like 6 minutes long, a really cute little clip. And I'll put the link to it Fusion page. All right. So back here, this is what is called a recursive sequence. All right. A recursive sequence is one that you need to build it up term by term by term. Whereas, for example, an explicit, the alternative to this is an explicit formula. An explicit formula is one where it isn't dependent upon the terms before it. You can find the 50th term just by plugging in 50, finding out what that value is. And there's some examples, there's some ones that I want us to be able to do. Right. Let's do a simple one. If I have 4, 7, and then 10, and then 13, let's first write this as a recursive, and then we'll turn it into an explicit. Right. How can I write this as a recursive formula? Right, you're adding 3 to it. Now, in order to play this out, you have to first define a base case. That's an important feature to begin, okay? And then, how do we go about saying that? How do I say add 3 to it? There we go. Take the number before it and add 3. Simple as that. So this is a recursive. Now let's see if we can do it as explicit. Let's see if we can do this. How do we get a explicit form? First of all, what kind of sequence is it? Arithmetic or geometric? Arithmetic. So start with the formula for an arithmetic sequence. It's a good start. And plug in what you know, solve for what you don't. Keep going a little further. And you wind up with this, which in reality doesn't really look like the original recursive very much at all, does it? And in fact, I wouldn't naturally think about 3 times a number plus 1 would give me that. But if you look at it carefully, it does. 3, 6, 9, 12. It is the same. It is the three multiplication table, but you are adding 1 to it. So they don't. It's not always intuitive how to get one out of the other. Okay. Let's try. I have some examples. It's kind of neat. Myself. Let's get for this one. It's like 8, 6. see if you can write. First of all, you have to determine if you're dealing with a geometric or an arithmetic form to begin with. So first, let's see if we can find out what the pattern is. What is the pattern? Is this geometric, arithmetic, or neither? Well, first of all, how can you find out? How would I find out if this was an arithmetic sequence? Do some subtractions, first of all. That would be one way to play it. So probably using the nicest pair of numbers that I have, these two pairs, because I'm only dealing with one. 9 over 8 minus 1 is 1/8, and then 1 minus 5/6 is negative. Yeah, sorry. I wind up with 1/6, which isn't really gonna fly for me very much. So it doesn't look like it's arithmetic because I'm not adding the same things each time, right? Is it geometric? How do I know if it's geometric? Yeah, do some divisions in that case. So if I take these guys, and then take another one and see if it flies. Doesn't quite look like it's going to fly for me there either. So is it geometric? No, it is neither. Okay. So what I want to be able to do is find a way to write this thing in some sort of pattern to be able to do this. So let's take a look. What do I have? Look at my denominators alone. What's going on? I'm adding 1 to my denominators. And then what's happening here? I'm adding 2. So how can I write this maybe in a recursive formula to it? First thing you're always going to do with a recursion is define your base case. And I'm just going to use X. Okay? Now, if I wanted the next term, my indices, what would the next term be? How could I write that? Crickets, guys. That's what I'm hearing. The crickets are doing this. Talk to me. Say it. Throw it out there. Okay. Yeah, you see, I see where you're going, but this is a single number by itself, right? And what you're teasing out of it is play with the numerator this way, play with the denominator this way. And what I'd like to be able to do is maybe express this guy not so much if I can't easily play with the number before it, because even if I said, it's not particularly easy to talk about just the numerator, okay, or just the denominator. Right. One thing that we can easily talk about is the index. So if I'm wanting the 15th term, I can write it out this way. So how could I describe, if you look at my indices, 1, 2, 3, 4, 5, and I look at my numerators, 1, 3, 5, what is this actually? 7 over 7, and we might even want to write that. Now we might be able to do it in a different way. How can I talk about my numerator now? 2, okay, say it again. 2, and let's use my index as n, minus 1. That'll fly. You could do that. Absolutely. What about my denominator now? How is my denominator and my index related? What is it? I can't read. Right. So it is, yeah. 5 and 8, 4 and 7, 3 and 6. So how do I write that? N plus 3. And that's it. Now, let's look at it carefully. Is this explicit or is this recursive? It's explicit because I can immediately plug in n for anything we want and get a value. It does not depend upon this term to begin with, okay? Because if I plug in 1 right here, what do I get? 1/4. All right, try this one. I think it was a little tricky, but we'll try a different one. Try this one on your own. Yeah, I just have to let them. Sure. All right. Now, there's a term that you need to learn, an arithmetic mean. And a geometric mean. Rather, geometric means and arithmetic means. So, for example, if I have A1, A2, A3, A4, A5, these are the arithmetic means. Okay? They're the guys in between terms. All right? And the geometric means are the same thing. Getting them is the interesting part. So if I give you 2 numbers and I ask you to find 2 arithmetic means in between them, for example, if I give you the terms, how about this? Now, there's a geometric mean and an arithmetic mean, not plural. there's a way to do them both. Sure. You might be thinking about when you were in geometry, you learned about a geometric mean, you take two numbers, multiply them together, and you take the square root. Not the same thing. So what's going on here? If you think about this, I need two of them. I'm looking for these two numbers. And what I'm really asking for now is how can I make an arithmetic sequence such that the first term is 10 and the fourth term is 100? Okay? So what you're really saying, if you're looking for an arithmetic sequence, is what the heck is this? See? Is he looking for somebody? Okay. That is really, yeah. Cool. So what we're going to do is we're going to find what fits in these spaces. Yes, this is a simple case, right? We can go back to this formula and say, hey, the first term is 100. The first term was 10. The difference is what I don't know. Yeah, this is a straightforward example. I'm using a simple one so we can put our brain around it. And now I have that's my D. And now once we have the D, we go back and we plug in what we need. And we wind up with and these are the two numbers I look for. Those are the two arithmetic means that I wanted. Does this make sense? So this is just another application of the formula. Now what we're going to do is we're going to do it for a geometric one as well. Let's pick something reasonable. Yeah. This is going to be fun. It'll be ugly. So this same idea applies. And we want three of them. Right? Ugly. Make life a little easier. Well, it's going to kill me if I make the numbers a little nicer. Okay, so using the formula for a geometric sequence, we wind up with Gn is equal to G1 R n minus 1. take the fourth root. We've done with that. Now you find your omega. Go in and find out what the next terms are going to be. So this would be times 3, so 30, 90, 70, and then another 3 geometric. So you might need, you're probably going to need to take some high order roots to do this, but that's not the end of the world. Yes. Good. Okay. Okay. First, deal with this. I have no idea what that is. Fine. Let's go with fine. Thank you. I'm just going to get these out of my hands now. I can't read those names. All right. So, thank you. I'm glad you could read those letters because that's actually we have enough time. All right. In fact, I am going to throw one formula at you and see how well it fights. Compounded interest. All right. This isn't as bad as it sounds. No, you're talking about continuous interest. Yeah, continuous interest is something like bacterial growth. Or, say, for example, half-life is continuous, even though it can be modeled within the screen. All right, compounded interest. Now, I often use the term A, so that's the amount final equals amount initial. A lot of other people use the letter P for principal. And I'll go ahead and do P just to keep everybody happy. So if I'm compounding quarterly, that means I'm compounding 4 times a year. So in that case, N would be 4. If you're only compounding every year, then N is 1. Now, you guys covered logarithms a million years ago, right? So you might wind up seeing a logarithm needing to be solved, needing to be used in one of these problems. If, for example, you're trying to get t, like the number of years, how many years would it be? Okay. We good on this formula? Can we move on? All right. Gotta love International Baccalaureate. Everything's in pounds and euros. That's sweet. All right. Jim put 1,500 euros. Oh, that is a lot of money. What is a euro nowadays? It's like what, 3 to 1, 2 to 1, something like that? Something like that, 2.5 to 1. Anyone been to Europe recently? Yeah, I was just there for lunch. It was great. Moving on. Next, $1,500 into a savings account that pays 4% interest, compounded semi-annually. All right. Semi is half of a year. So n in this case is equal to 2. After 10 years, how much does he have? Crunch it. This is a straight plug and chug. Did I say 1 minus or 1 plus? I said 1 minus, should be 1 plus. My fault, 1 plus then. Because well, first of all, it should be a plus nonetheless, but the reason why it's 1 plus it is because if I actually distributed this p into this term, and once I've crunched my number, the point is that what, because I have my n times p, I have to do my exponent first. But this r over n is just the interest piece, whereas the 1 is the original principal. Yeah. Compounded interest occurs on a schedule. Like every X number of months, whatever's in there, we do it. Whereas continuous interest is growing all around the clock. Okay. Semi-annually means that on July 1st and January 1st, we will give you more money. No. Whereas continuous interest, if we come back in 5 seconds, you'll see a different number. It'll be a small change, but yes, got an answer. Yes. Okay. Well, what I really want in this case is, this is 4%, right? So what I want to put in, well, let's try both cases and see which one makes more sense to us. 1 plus 4 all over 2. So now 1 plus 2, and now I'm tripling my money each and every time around. That I don't want. That would be fantastic if you had a bank account. Yeah, that might be nice for you. But now it's 0.04 all over 2.
Oh.
And that's what I want. I want to express it as a fraction. As a decimal. Yes, sir. Yes, they do. What? Yeah, then things would change. Then your principal is going to change. Okay. And then what's happening is it's going to grow faster. Like, for example, in a retirement account. All right. Like, for example, I get a certain amount of money taken out of my paycheck and goes immediately into a retirement account. If I teach until the end of time, I might have something to retire on. But the idea is that I'm adding to the pile every paycheck. So it increases not only with the interest, but it increases also with me depositing new payments into it. What's that? Yeah, it changes the P each and every time. Right. So we wind up with this, and n times 10, and my principal is 1,500, and this is a straight calculation, and what do we wind up getting? $1.02 to the 20th power You're gonna need a calculator for that job. $2,228.92 euros. And you're done. All right. Sound good? Fantastic. All right. So, just give you a couple of quick assignments, really quick. This isn't going to take you too long at all. What I'm about to give you? Homework. And how about this? Yeah, I'll put it up on Fusion. Okay, I'll post it on Fusion, and I'll give you some time to work on it. This episode of the Bronco Show has been brought to you by the Fibonacci Sequence.